Let's talk about the library method and library search, the heart of the library method. Let's examine the library method library search tab. That provides me tools to pick the library I'm interested in. So for example, I could change that library, I could remove that library, and I could decide to add it back. So if I look at this addition script, I can see the formats that are supported. There is the MS library format. There is, I can put a reference library, we'll talk about that later, a pattern reference library. I can also pick a PCDL, which has the extension CDB, and I can read in a NIST library in the format of a .L. So let's do that. Let's load in the NIST library. And you can see I can put it back. I can move things up and move things down. Alright, I can also open a library. So here I've got the NIST library. I can open that in the library method editor. And here I've got all the NIST entries in that very large library that I can examine. Next, let's take a look at the search criteria and the pre-search types. So there's none, which would just examine each spectra and compare it. I wouldn't suggest this unless you have a very tiny library, and then normal and fast. So let's take a look at what those options mean. In the definition, normal, which is the default, screens the entire library and basically 0 false negatives. And then there's a fast option, which has a very small false negative rate but gives you a speed of 100 to 1,000 times faster. So if you're searching very large libraries and you really need the speed, you might consider the fast option. Next, the adjust score option. And if we look at that definition, you'll see that this provides NIST compatibility in terms of the score, because it weights it in the same way as the NIST algorithm in the dot product calculation. It's worth mentioning that the spectra are compared using a calculation called a dot product, which is a cross product of two vectors. You can think of the dot product geometrically as a projection of the cosine between two vectors. Let's take a look at the definition of different kinds of library searching. Reverse library search as a term in this definition here shows you that it's the process of taking the peaks in the reference spectrum and looking for them in the actual acquired spectrum that you're comparing against. It's useful when there's a lot of noise ions in the acquired spectra and you're looking for that reference. If you just look for the ions in the reference, you can get a much better score. There are places where reverse library match works very well. So you might ask, where do I see reverse library match scores here? I look at the match factor. That is a combination of the library match score and the retention time penalties that we just talked about. Now, if I want to adjust the library match score, I can do that, but not here in the standard. I need to go to the advanced section, and here you see a table of the values for standard, but some that are not shown. So for example, the pure weight factor. The pure weight factor controls the extent. The default is 0.7, same as used in NIST, and that is a hybridization of forward and reverse. If I want reverse, I can change this to 0, that would be reverse, and now my searching is going to happen in the manner that I described with the reference spectra looking for ions, and that behavior can be very useful, especially in noisy spectra. Next, remove duplicates. So when components are found and then searched in the library, it's quite possible that a component could hit on a library, especially with a large library like NIST, with a lot of spectra that are quite similar, that there would be duplicate hits for the same component. So this is going to delete hits that don't have the best score. So you're left with each component with one hit. Let's go to the official definition. This is a case where only one component is given a single hit. Let's discuss retention time criteria in the library method. Now this is incredibly useful in terms of reducing false positives if you have information about the chromatography of when that component is expected. So if we're going to use retention time match, we have a number of choices about how to penalize the library match score if it isn't at the time location that we're expecting. The choices here: Gaussian, the default, that's what I typically use. There's trapezoidal penalty function. Let's look at the definitions. First, of course, there's no penalty to the library match score. We can penalize from a Gaussian penalty function, as shown here. And then we can also penalize from a trapezoidal function, which has much steeper drop-off point in terms of does it appear in this window. Next, how the retention time mismatch penalty is applied. You can multiply, you can add, and then there's a maximum. So if we look at the definitions here, you can see that's the largest penalty, and here is the definition of the multiplicative approach and the additive approach to the penalty of not fitting that component right on the expected retention time. Last, retention time calibration file, which is a mapping between retention indices and, through a calibration, hard retention times. Basically, you're expecting that hit to appear at a particular retention time. And the formats that are supported are a CSV format or an RTC format. This is the shipping RI-PEST matrix, if you wanted to try that. This mapping will dramatically reduce false positives because you know there's a constraint now on the possibilities of that component hitting the library. There's time constraints, chromatography constraints. Thanks for your attention.